All right, let's go ahead and pick up where we left off with hash tables. If y'all recall correctly, a hash table, we are using it to map one item to another. And the issue that comes up, let's go and step back. And so let's say you have your hash table on the left, you have insert 2 goes to index 2, 21 might go to index 1, 34 go to index 4, but now you're trying to insert 35. Where does that thing go? Anyone? How do we do it the old way? My old way.
No. Yeah, you put it.
Oh, we're talking about hash tables.
Like we would add it.
Add it to
The linked list.
which is a chain, right?
Yes.
So we add it to the linked list of it, which is the chain. So our first solution to this, and when we have a collision, is the problem. There's 2 ways to resolve it. Yes, slides. The first one is hashing with chaining, aka separate chaining. Every hash table actually is a pointer to a linked list or a chain. And then you just add it to the linked list. So when you want to search something, you search the linked list.
That's like our first project. How we originally thought of doing it.
Chaining.
Similarly, but not quite.
Isn't that the whole trick?
Everything in this class.
So what? Similarly, but not quite?
No. Isn't that the whole trick to the first project? I just chaining.
Yeah, you could chain it all the way down.
Chain.
Chain. Okay, no.
Chains.
All right. The next, or another common solution, is hashing with open addressing. Instead of having a chain, every entry contains 1 key, and when you have a collision, you need to find an empty entry in that hash table and put it there. Does that sound easier or harder? Harder. Okay. So let's see. Well, we're going to talk about the chain real quick. If you recall, if you had your 34 in, you add the 54, it goes right there. You had a 101, you just add it to the chain with the 1. Awesome. We talked about the runtime is in general O of 1 unless everything hashes to the same location, which is bad. Oh, did we talk about the hash function much?
No.
Oh, really? I don't think that's the case. Let's find out. Let's see who's the who is telling the truth, me or you.
3:20 every day, and then I have my 2 night classes.
All right.
I think next semester is going to be a lot easier.
Oh, we have a hash function right here. Right there.
Right there.
Right there. Yeah. Right there.
Right there.
What does the hash function do?
Ash's thing.
More specifically.
That was the location.
Oh,
No, it was that key value that we had. The not the location, but like what number it mapped to.
Mm-hmm. Okay, figures out what number in the hash table it maps to.
Yeah.
Good.
That thing.
Good stuff.
Yep. You're getting that. It's the thing with the stuff.
So this one uses modulo, key mod m, where m is the size of the array. That's pretty good. You can do a multiplication method where it's key times some fraction, mod 1, times the array size, mod m. Why would we do it that way? All right.
Is that an actual question?
Yes. Okay. Just to change it up a
What does
little.
mod do?
Anyone, what does mod do?
Mod is mod.
It returns the
Oh.
remainder.
Returns the remainder.
So it's the actual modulus.
Really?
Yes.
Why does it?
Yeah, it returns the remainder.
No, it was like modulo and then mod. They were the 2 words.
I thought this was kind of common sense.
Well, I know what modulus does, but
Modulo and modulus is the same thing.
Oh, modulus and modulus. Mod and modulus, same thing. We just call it mod.
Oh yeah, so it's modulo.
I'm going to break this thing because I'm just going to keep playing with it. Let's see, and then you create a hash method, which is what Java does. Because every object has to have a hash. But we're not talking about Java, are we? We don't care about that.
Java.
Java. Who
Nobody cares
uses
about Java?
Who uses that language?
It's used and abused by new and inexperienced programmers.
Right. So, for example, if all our keys are multiples of 5, 5, 10, 15, 20, 25, 30, etc., and evenly distributed from 5 to 25, and we do mod 7, the key at 0 would have a total of 7 items. Right? What's 5 mod 7?
2.
Okay. No.
No.
We'll try that again.
0.
What's 5 mod 7?
Here.
5.
5.
Oh, yeah.
5.
I never knew that it did that because
What's 10 mod 7?
3.
There we go. Now we got it. 15 mod 7?
8.
8. 1.
No,
Wow.
Where do you get 8 from?
Don't even know.
I'll be right.
25 mod 7? 4. 30 mod 7?
2.
2. And then what's the next one? 35 mod 7?
0.
0.
0.
Did we go through all the numbers there?
Sure.
49 mod 7.
I think.
Or did we skip 6? We missed 6. When does 6 show up? Where's 6? What's 40 mod 7? That's back to 5. Yeah, we missed something. Oh well.
Not important.
Okay, now what if m was 5? What kind of distribution would we have? What's 5 mod 5?
Here.
What's 10 mod 5?
Here.
What's 15 mod 5?
Yeah.
So where would all the items go?
Here.
Do we want that?
No.
It was 20.
Zero's like some crazy one.
We missed 20.
Oh, 20, that's what happened.
Sorry, I was bothered by it.
Thank you, Jonah.
It was funny.
You did your work for today.
Awesome.
We're-
Joe doesn't just walk out. I'm back, guys. Later.
All right, I'm out. Got my A for the day. All right, keys are non-random parts of numbers. Use all the data. Okay, so the idea is that with your hash function, you want to make it a little more complicated than just modulus because you want to try and randomize out where everything is located. So you want to use as much of the data to contribute to the hash function to get a better distribution. A common thing is called folding. So the sum of the natural arbitrary groups of digits. Ooh, this is a good one. I like this one.
Pictures.
Now I need a nice
Violent.
Violet?
Yeah, you're just throwing chairs around.
I don't think that's throwing. I think that was a rolling.
You're pushing it.
Don't question it. I am not
You're
questioning it.
pushing it.
I am.
Yes, don't question it.
I'm not questioning it. I'm just explaining the situation.
Mark your glare.
Wow.
Well, we keep running into the issue of going into the glare.
Oh man.
Instead it's a terrible box. There we go. Now it's a linked list.
I know it's a no.
It's a linked list.
Now it's a
Again,
box.
you have the linked list.
All right. So if we had, give me a number, long one, 9 digits, maybe 10.
1 million.
5,000.
7,064.
Ow, that worked.
I don't remember what I said.
9365.
All right. So if we wanted to fold this number, we would take these 3 right here, these 3 right here, and these 3 right here, and then we add those digits. Whoa.
Magic.
Got it?
What if it didn't have that many digits?
Like if it only had what, 2 digits?
Yeah, like it had some like weird number.
Like 29? Then your folding would take the 29
Okay.
and add 0. Or you could add the 2 and the 9, but that seems kind of super silly, right? Okay. So that's folding. Don't use non-data. Yeah, don't use checksums. Do not use information that might change. Why wouldn't we want to use information that might change? Oh, that's a great question.
Because then the stuff would change.
The what?
All the the values would change, and then your key would be different.
Yeah, your key would be different. We don't want the key to change. We want the key to always be the same.
You like keys that stay the same.
Yeah, you want to have constant
It has
keys.
to be able to fit the lock.
Right.
If they don't fit the lock, shoes on the wrong foot.
All right, open addressing. So you might have a hash table similar to this, but you have two objects, object 3 and object 2, that both map to index 4. But when object 2 was put there, I don't know why it's done in this order.
Because they're dumb.
They dumb. It was pushed down to index 3. So we've studied hashing with chaining, which is hopefully easy to understand. Anyone have? But if not, maybe open addressing will help you. Another option is to store all the items, references to single items directly in the table. So you have to come up with a way to handle collisions. So it's first mapped to the array cell using the hash function. If there is a collision, find an available cell. And how do we find out which cell we want? Let's go create a little example on the board.
Yes.
There in chapel today?
So 1, 2, 3, 4, 5, 6, 7. What?
Yeah.
So I'm not seeing the whole time.
So where would 5 go? Where would, let's try 15 go? For modding it by 7. The 15 spot.
Just kidding.
Alright, let's go put 21. Where would that go?
0 spot.
Let's go put 35. Where would that try and go? The 0 spot. Alright, so where should we put it? We're not doing chaining.
So we
You want to put it in the next one, okay.
Why not?
Okay, we'll put it in the next one. 35. Alright. What could be a problem with this?
So if they were to think about it, like, well, that should have been in 0 spot. Let's look for it there. Oh wait, it's not there. Where is it?
Next spot.
Okay, yeah. So if we want to do a get of 35, we would first look here, right? It's not there, so what do we need to do?
Go up the
Go down the array. Check there. If it's there, yay. If not, we have to keep going, don't we? Until we find something that's empty. Okay. All right, so that kind of makes a little sense. What if we do this? What if we remove 21? All right. And now we want to do a get on 35. Who knows? Oh boy.
I knew there was going to be problems.
So would you overwrite the 21 with the 31?
What if you made the 21
But then you wouldn't be able to find the 21.
What if the 21 pointed to something that contained everything else?
Well, that'd just be chain. We're not doing chain.
That isn't true.
The common way you actually solve this problem.
It's easy.
I'm glad you think so. What is that method that is so incredibly easy?
The one that you're about to show someone for.
That's correct.
Give it to another programmer. Make sure it's a junior developer.
Yeah. Look at yourself as.
All right. So that would be you.
You're evil people.
Go ahead, Craig. I can't wait.
I was only making a joke.
No, okay. No one? Okay. When you delete something when using open addressing, you mark it as deleted. meaning that if you try and get something that's been marked deleted, you continue on.
That one's
What
easy.
chapter is the heap covered in the textbook?
That's a pretty
It may not even, I don't think it's in the textbook.
good. Oh boy.
Joy.
Yeah, I don't know why they never cover heaps. It's quite silly.
That book is useless.
It covers graphs, though.
The textbook's actually really helpful.
Right, when it covers what it needs to, but yes. I don't know why it doesn't do heaps. Why doesn't it do heaps? Why doesn't it do heaps?
Maybe the person didn't like it.
They're wrong. Alright. So what we're doing is linear probing. Because we just go down linearly. What else could we try and do? Instead of going down linearly, we could try and go down.
Iterative.
I thought you said intervally. I liked it.
Hit the bully.
Intervally.
Only 8:48 in the morning.
Yeah, but I was up half the night.
For what?
The storm last night.
Was it a storm
last night?
There was a storm last
It was
night?
hailing last night.
I passed out at like 11:30.
Yeah,
It was
I,
hailing?
I fell asleep at like.
Were they
11:50,
hailing your
12 o'clock.
name or just?
No, it was like.
Wow. Wow.
We were doing terrible puns earlier. I was just continuing. Keep it going.
It's bad. Yeah, it woke me up at like 12:45, and we were like, "What the heck?" We were like, "Is our window open?" No, it was just hitting the metal outside the window.
Oh, you are.
So wait,
the
it did
third
rain.
building.
Yeah, I am on the other
No
side of the
clue.
building.
I'm like
on the
Jonah.
building that faces
I
the
didn't
big
know.
open space.
Now, okay, did it just thunder or did it actually rain?
Both. It was hailing and raining and thunder and lightning, and it was gross.
It was gross.
Gross?
Yes.
I've never actually heard a thunderstorm being called gross.
I had no clue it rained last night. Wait, yeah, did it really rain last night?
Yes.
Oh, that's funny.
I had
'Cause
no
we had to
idea.
inside the softball field when we got back from our game yesterday at 8:30 when it's dark outside, and then it rains.
Yep.
Really, my roommate's called for here for the whole night.
All right.
I'm gonna laugh. So.
So
hard.
instead of linear probing, what else could we do?
Regular.
Oh You're nuts,
I didn't
Makes
say
me think of aliens.
Regular probing.
You know what? Let's just forget it. I didn't say.
It's recorded. We can't forget.
No, it's
You
not.
can't
It's
forget.
not recorded.
I can't stand up right now.
We can get the boys at the office to edit.
All right. In math, you have linear functions. What other functions do you have?
Quadratic.
Quadratic. Right.
I was just gonna guess that like as a joke. I didn't.
No, that's the answer.
Wait, you
That
got
was the
As
answer.
opposed to
Wait, you
mine.
can guess quadratic.
Look, I'm not joking. It's even on the slides.
What? What? Now who remembers the quadratic formula?
Screw that.
You know, this is probably the best class ever right
I
now.
love this class. All right, so you basically go 1 and 2. You skip 2, then skip, I guess 4, and then skip 8. Or no, that's exponential. You just skip every. You just multiply it by 2 each time, right? Pikachu. Good job. And why would we want to do quadratic probing over linear probing?
I'm like,
Because we're aliens.
Yes.
Do you think C++ can be a bit sexual sometimes? And that is No. recorded.
That is true. When you declare 2 classes to be friends, it's really, you're giving benefits to the other class. Wow, that's pretty bad. All right, anyway.
Some classes are friends with benefits?
Yes, that's,
What?
yeah. That's why you never have friends in C++. Friends are bad. Friends are terrible in C++. All right. Why would we want to do quadratic probing in a hash table instead of linear probing in a hash table? What would that help us avoid?
Never gonna get old.
The weirdness that we just did where we put the 35
So you're doing linear probing. How close is the next item to the one you just put in?
Correct.
One.
Very close. If you do quadratic probing, is it right next to it or farther away?
Farther away.
So what would that? Why would we want to do that?
Because then if you'd be able to like see where it actually went, it wouldn't just be the next one. So we wouldn't have to deal with the whole marking and all that mess. Right?
No, you'd still have to mark because what if? Yeah, you could still delete it.
But if like you had something where that would have to go in the one spot like 35, you would actually still have that spot open. 'Cause
Sure. Yeah. So what does it avoid?
overriding and pushing things everywhere.
So the point is, if you're doing linear probing, you're going to start forming clumps of a lot of items. Quadratic at least tries to distribute it throughout the array.
Ah.
Are we done using the keyword today?
No.
Double hashing is if it fails the first time, hash it again with something else. Come up with a second hashing function.
That doesn't sound fun.
So linear probing, choose the next available array. Be sure to wrap around the end of the array. The array is full. You need to throw an exception or just resize the array. Really, you need to resize the array. Quadratic probing, variation of linear that uses a more complex function. You mean quadratic function to calculate the next cell. Great. Double hashing, just apply a second hash function after the first. Make sure it's different and don't generate a zero. Great. Add a step size. That sounds even better. Ooh, a load factor. So what else could happen here that would not happen if we were doing hashing with chaining? Let me go back to this. Let's give me another number to put. Any number.
26.
15.
We already put in 15.
16.
16. Where would 16 go?
1. No, 2. 3.
How about another number?
17.
17. Where would 17 go?
Right where the 5 is.
Down here.
So down, yeah.
Oh.
How about another number?
18.
18. Great. How about another number?
This is a mess.
21.
21.
What are
We
we
already
chicken
did
dinner?
21.
Where would we put it? Oh, we already did 21. We can't do it.
26.
26. Wow.
What?
Whoa.
Ooh, that was weird. All right, where would that go?
Resize the
Resize. Ooh, we have to resize the array.
Yep.
That changes the runtime, doesn't
Yes.
it? Is that okay?
Yes.
Okay.
So we have to resize the array.
We're not dynamically allocated.
So we have to resize the array and put it in. Okay, that's normal. What did you notice as the array started getting full when we were trying to put something into it?
That if you take the module 7 and if the remainder is already has something in the index, you add it to the next one.
Right.
There's available space.
Linear probing. But that it means that you're doing you're having more collisions. So as the hash table fills up, you're having more and more collisions. Do we want collisions
No.
when we're probing? No.
No.
It's fine. It's fine.
So what we do is we have something called a load factor, where basically we will say if the array is ever 80% full, increase the size.
By how much?
To make it so it's no longer 80% full.
20%?
So would you just double it?
Doubling is usually the easiest thing,
Okay.
or increase it by 50%. I think most of the time with hash tables it's 50%. So that's what a load factor is. It's just there to help us avoid all these collisions. So for open addressing, if you're less than 50% full, you're wasting actually a lot of space. So you want your load factor to be somewhere above 50%. If it's over 80% and usually have way too many collisions or overflows, collisions, so that's usually something you wish to avoid. For chaining, it's a little different. Less than 1 is wasting space because you have a chain, you can always add more items to the element. And greater than 2, the searching of something starts to hinder performance because your linked list might be getting pretty long. All right. So deletion, must use lazy deletion. What is lazy deletion?
When you leave a mark
Lazy
there.
deletion.
You have to leave a mark.
Yeah, you just leave a mark. You don't actually delete it. You say, oh, this has been deleted.
Bye.
Yeah, that's lazy deletion.
There it is.
There it is.
Programmer style.
All right, let's see what these graphs are. Successful search with linear probing, double hashing, and separate chaining. Huh. What does that tell you? It tells you linear probing is very slow, and chaining is a lot faster on the searches. And successful search, what's the difference? Oh, with a load? Oh, that's successful when you actually find the element. This is if you can't find it, because it has to search the whole array. What it's trying to tell you is once your load factor gets over here, trying to search your hash table is incredibly slow. So that's why you want your hash table to be less than 0.8 full, or 80% full.
You want it to be the green line.
The green line. But what is the problem with the green line?
It's a bad green.
Hmm?
It's a bad green.
It consumes more space because you're doing chaining. Although that's not necessarily the case, but in general, that is the case.
So which one's the best? This one?
Sure. Depends on your situation. When should you be concerned? Normally you shouldn't, because usually your library is going to implement these things. But of course, for our data structures class, we're going to do both. But if you wanted to decide which one to use, if you know the number of items to be inserted into the table, then you can probably just create a, something with open addressing and call it a day. If you have plenty of memory, maybe just make it with chaining, call it a day. Do you know the expected load factor? Do you know how fast search needs to be? That may go into deciding between open addressing and chaining. All right, Java. Let's see, load factor is 0.75. That's nice. Oh, that's it. Okay, great. Any questions before we code? Nope. All right.